Any other pressing questions before we get going? Okay, so the good news is that I'm already behind by 1 page, which is not crippling. That's just where I want to be. So let me just get the next set here. Yeah, so thank you so much so far for the engagement. Fantastic. I was having a great chat outside. You know, again, please make sure you corner me and all the lecturers. You know, I made this long trip to come and chat with you. So so please, really the lecture is just a part of the experience. I really am available and would love to sit over lunch here about what you're working on too. And I can tell you other things I'm working on. I'm delighted to talk about anything. And so don't be shy already. All of you are being really open and amazing. So thank you. Good. So let's get into back into this. So I drew this picture of maybe let me just draw it again. Okay, so we're talking about this conceptual idea. Okay, HEFT, SMEFT, and the standard model. Okay, and so I wrote all these formulas in the last lecture. I gave you parameterizations in these Cartesian coordinates and these polar coordinates, and you're sitting there like looking at me like, what's the big deal? I mean, we all know how to make coordinate changes. It's just algebra. Okay, so let me show you that it's not obvious. So I want to take. So again, I really want to ask. One way of asking the question, which is going to be the theme for me all week, is, you know, what theories live here? Okay, what's the difference between this region and this region in this sketch? And so the first step to answering that question would be to just write down the map between these two Lagrangians, okay, and see what happens. So let's do it and see what we get, okay? So we have SMEFT versus HEFT. And so just say again, we have this capital H, which we can write in terms of phi fields, okay? And we can write the relation, which I don't think I wrote before, between phi and the polar coordinate fields, okay? Just looks like this. Notice here, only in this one moment, I'm going to be careful to distinguish, we'll call it V naught versus V that I was writing in the last lecture, okay? In principle, those are two different parameters, and there are models where those can be two different parameters, which will eventually, I'll at least mention, okay? So keep it in mind, maybe even think about how could I build a theory where V naught that appears here is different from the V that appeared in those previous formulas, okay? So here I mean V sets the gauge boson masses, if you like, the fermion masses, okay? V was the thing that appeared in the mapping, in the normalization of the pion fields, of the Goldstones, okay? So that's what I mean by V, right? That's, if you like, the scale of the nonlinear sigma model when we break electroweak symmetry. V naught is here in this shift, okay? Going from the origin in field space to the physical vacuum. And there's a really interesting question that we're going to spend probably half a lecture on or something. So again, keep in mind, how do we tell in HEFT where V naught is? And this is actually something that Rodrigo and collaborators figured out in one of their papers that I reference at the end of my lectures that you should definitely read if you're interested in this stuff. We'll come back to this. I'm going to give you their argument later in the week, okay? For now, actually, I'm going to set V and V naught equal, okay? Just because I already have enough to write and enough opportunities to make typos. So, so I'm going to make my life simple and make those equal. If you want to see where all the V naughts go, you can go look at our paper or try to figure out the differences yourself. Okay, good. So let's start by just writing the operator mapping for these operators that appear in these low dimension versions of HEFT and SMEFT. Okay, so here's a dictionary. H squared is 1/2 phi dot phi is 1/2 v plus h squared. dh squared is 1/2 d phi vector squared is 1/2 dh squared plus 1/2 v plus h squared dn squared, and dh squared squared is phi vector dot d phi vector squared is v plus h squared h squared. Okay, so that gives us a dictionary to go back and forth between capital H and little h. Okay, this is just plugging in these relations. Okay, so then I can write L heft as 1/2 k of h squared dh squared plus 1/2 vf of h squared dn squared minus v of h, plus, of course, higher dimension operators. And we can rewrite this v squared f squared over 2 dh squared. Oh. Okay. All I did was plug stuff in. Okay. This is a nice little exercise. If you look in my notes, I'll try to mention them, but I mark a bunch of little things that I think are worth doing if you're interested as exercises. So just convince yourself, because this may seem radical, okay? But notice weird looking terms like this, okay? So I have 1 over capital H's in this just kind of trivial mapping going from the HEFT Lagrangian to the SMEFT Lagrangian. Okay? So I keep saying this word analytic, and this is one of the key signs of non-analyticity in a Lagrangian, is just finding inverse powers of a field. Okay? Now, if there's an obvious resolution, and EFT Lagrangians, and again, we'll talk about this a bit more, this will be a reoccurring theme. EFT Lagrangians need to be local expansions in terms of fields and derivatives. So I can't have anything like this. This does not give me a local expansion, okay? This actually has a physical interpretation of exchanging a massless particle. We'll kind of come back to that. But in this map, we know this map must exist for a wide class of theories. I mean, I drew those circles, so it must be true. What's going on here? Well, of course, F is a function of the Higgs 2, okay? So there's gonna have to be some appropriate powers of H squared in here to cancel this non-analyticity if this map exists, okay? So it's not, this is not like something particularly deep, but the reason I took the time to write this is because I wanna really emphasize that it is completely, it's not an obvious thing how to do this map, okay? And it's gonna even get worse, as we'll see soon, okay? There are even trickier bits to trying to make this map and get from SMEFT to HEFT, okay, to go back and forth. So just to say, and what's really happening, again, one of the things I want to emphasize to you is that these effective field theories really conceptually are different in the sense that HEFT, if we start with HEFT, we're really reorganizing or resumming an operator expansion that is different from the way SMEFT is organized. And that, again, I think is highlighted by just this sort of simple algebraic exercise, okay? So we see non-analyticity, Okay, and that's weird. Okay, so we should worry about that. So I'm just going to leave that with you. Yes. Well, I mean basically the same. So good, very good. So notice I didn't call this equals SMEFT for exactly this reason, okay? Indeed, if this non-analyticity were physical, or there were non-analyticity in here, as you say, which it could be, then I can't call this a SMEFT, right? This would, in that case, right, this would live in that band, indeed. But if I can make it all nice and analytic and a local expansion, then I would call that a SMEFT, okay? And that's exactly, basically the question, okay? Excellent. Yeah, absolutely. There would be even more, I would have even more operators here, absolutely, and then I would get more stuff here, indeed, yeah. But you can see already kind of at the leading order, there's something confusing, okay? So, you know, it's good storytelling to set something up and then make you wait. So we're gonna come back to this because I have to tell you, we have to digress for a little while, and I have to tell you something that makes this even more confusing, okay? Because I really want to try to motivate you to hang in there with me when I introduce geometry, because it may feel like it comes out of nowhere, okay? So I think it's important that you really understand why we're gonna take the time. So the next thing I wanted to do, okay, I am worried about time. The next thing I want to do, I'm going to do this kind of quickly. And by the way, again, everything is in my notes, which I will make sure get posted today, okay? So you can, if I start skipping details for time, okay, or being a little bit more schematic, you can see more details in my notes, and you can always bug me or look at the references. So I want to tell you a little bit about a very important property of QFTs in general, okay? Something I'm expecting you've probably heard, but you maybe have never seen the argument, okay? So, so that is the fact that we are allowed to do field redefinitions in quantum field theories, and that can completely change the way the Lagrangian looks, but don't change the observables, namely the S matrix elements, okay? This is, oh, we're in lecture 2 now. I forget what I called it. Field redefinitions, something like that. Okay, so really field redefinitions are going to be very important for us. And so I think it's worth the time because it's such a critical component of the discussion we're going to have today. I think it's really worth the time to at least show you some details for the argument of why field redefinitions do not change S matrix elements, because it's really, frankly, surprising, okay? But the physical picture is that we introduce these fields as a tool to construct local Lagrangians, okay? So, you know, in quantum field theory, there's always this tension between wanting to make locality manifest, okay? In which case we work in terms of fields, or do we want to make sort of the quantum mechanics manifest in terms of particles, right? In which case we use Fock space and states and so on, okay? And of course, we know a mapping between the fields and the states, right? The S matrix elements, for example, are computed in terms of the scattering of particles, okay? That's the physical stuff that we measure in the experiments. But writing down a local theory, a local relativistic theory of quantum mechanical particle scattering is really hard, okay? And that's why we invented these objects that we call fields in order to allow us to easily construct theories that satisfy the sort of fundamental properties of special relativity, causality and locality in particular, okay? But that comes at a cost, which is that the field is really not a physical object in itself, okay? It's a tool that we use, and because of that, the way that we choose to parameterize that tool, that's a human choice, and as it turns out, if I make one choice and you make a different choice, and we go and we calculate, the physics isn't going to care, okay? We're going to get the same answer as long as we're following all the rules of EFT in the way that we construct our Lagrangians, okay? This is a really highly non-trivial fact. If you've ever tried to check it, you know it's actually quite tricky in practice to see this happen. If you've never checked it, it's another exercise I put in the notes, and I'll mention it in a moment. But let me just give you the argument, and again, being aware of time, I don't want to go over too far. So let's just talk about the field redefinition invariance of the S matrix. And so by the way, this is something I think is so important, you know, with my collaborators, Dave and Xiaochuan, we recently put out a long paper on thinking about this, and I think there are, I mean, I don't understand this, let me put it that way. I'm gonna give you the standard argument, but I'm not gonna claim, well, I'm not ever gonna claim, frankly, to understand much of anything, but I think this is actually very, very subtle, and there's potentially still, I don't think there's anything new to really discover. I think that this lore is true. I have no reason to believe otherwise, but really understanding where it comes from is, I think new perspective will be valuable, especially again, as you'll see, the reason I'm bringing this up is because it deeply connects to this picture of geometry, okay? All right, so one way that we get S matrix elements in quantum field theory, right, the quote, better way, is to use LSZ reduction, okay? So I'm gonna assume that you are familiar with that. If not, bug me about that outside of the lecture. I need to assume that you've seen this. If you haven't, please corner me at some point this week and I'll talk you through the idea. But basically, you know, we get amplitudes or S matrix elements by doing this LSZ reduction procedure, which schematically looks like the following. So we have some product, right? This is a product over all of the in and out particles in our theory. Those just change the signs of the momentum. And then we weight this by inverse propagator factors. Okay, where these are inverse propagators in position space. And then we extract the non-trivial information from the connected correlators, okay, which we get from the path integral as follows. So if we write Z as a functional of J, okay, we're doing the path integral over fields, e to the I action, plus this source term, and then we write Z of J as e to the I W of J, right, where this W, this is just by definition, but this W generates for us the connected correlators, okay? Again, I'm assuming you've seen this. If not, I apologize. this is in sort of standard, in all your favorite QFT textbooks. Okay, so we can extract the connected correlators as follows by taking functional derivatives with respect to this source. And then, actually this is missing from my notes. So we set, well, what notation did I use? Okay, actually maybe this is fine. Okay, so this gives us some generalized connected correlators with these sources turned on, and then to get, basically to put the equations of motion on shell, if you like, we set the sources to 0 to get the correlation functions, okay? So this is a sketch of the LSC reduction of the sort of the full story of quantum field theory in 2 blackboards, okay? Getting from QFT to S matrix elements, this is the procedure we use, okay? And this projection is basically picking out, what is this doing, right? This has a bunch of poles in it, and this is basically picking out the poles where the external states are going on shell, okay? So there's a lot of extra stuff in here. By the way, that stuff changes when we do a field redefinition, okay, as I'll emphasize in a moment, but the correlator is non-invariant under field redefinitions, okay? It's only when we do this LSZ reduction that we get something that's invariant, okay? So that's sometimes a point of confusion for students, but we really claim, at least in this standard perturbative quantum field theory, that the physical quantities are these S matrix elements, okay? The correlation functions don't have to be field redefinition invariant. In fact, they're not. So let me show you what happens when I do a field redefinition. And by the way, let me, because I keep talking about coordinates, right, in the last lecture. So we are talking about Cartesian coordinates, polar coordinates, and we know we can make coordinate changes back and forth, right? We've been doing that since grade school. And so here, okay, I want to equate the idea of coordinate changes to field redefinitions, okay? That's just a fancy name for a coordinate change. So let's write one down, a kind of a generic field redefinition. So we have phi of x is some function f of phi prime of x, okay? So this is like, you know, phi goes to, you might just say, as an example, phi of x equals phi prime of x plus, you know, some coefficient, phi prime of x squared. You can do whatever you want. You can have derivatives in here if you want, although we are not going to do that in this set of lectures for reasons that will become clear later. But, yeah, that's prime, right? So you just have some map between 2 variables, okay? Nothing fancier than that. That's all I mean by this formula, okay? Does that make sense? So then we can plug this into the formalism I wrote over there and just see what happens. So let's do it. We get a new Lagrangian. Okay, so L of phi is L of f of phi prime. Okay, I'm just plugging in the field redefinition, and I'm going to call that L prime of phi prime. Okay, then I can put that into the path integral. So now I get z prime of j is integral d phi prime e to the I L prime of phi prime plus j phi prime. And that's equal to integral d phi e to the I L prime of phi plus j phi, okay, where with the integral, sorry. Okay, the integral, of course, is an integral over space-time, right? Because I need e to the I action. All I did here was relabel dummy variables, right? Integration variables. Okay, so I'm going to call this thing z prime, which is the path integral over the phi prime fields with the phi prime Lagrangian, coupling phi prime to a source, okay? And then just to make the argument really clear, I'm going to relabel it I'm just going to call it something else, okay? I did not do a field redefinition here. I'm going to do that in the next step. So now we can compare that with taking our original path integral and doing the field redefinition, okay? So we have z of j, which I think is, I left, okay? So z of j is there, right? As opposed to that, what I called z prime, right? That was the path integral for the prime fields. So now I take z of j and I do the field redefinition. And what I get is the path integral over the prime fields. I get a Jacobian factor because I did a change of variables and an integral, okay? So this is a Jacobian. And I get e to the I integral L prime, phi prime, plus j f of phi prime. Because again, what did I do, right? I replaced this by f of phi prime, and I replaced the Lagrangian in here by L prime of phi prime, right? So this is honestly doing the field redefinition. No, I haven't changed j, right? That's just some external source, right? So it's, I'm calling it j here, I'm calling it j there, but the point is, exactly the point is that j couples to f of phi prime in this path integral, but it couples to phi prime directly in the other one. So that's exactly the difference between these two, okay? So I'm just going to tell you that you can ignore this Jacobian, okay? It is, we could talk about it. This is I think, again, well understood by experts, maybe less well understood by me, but nonetheless, the Jacobian is, so the Jacobian equals 1 if we use dimensional regularization. And this is just kind of a technical thing. By the way, this same Jacobian leads to the anomaly in the Fujikawa treatment, if you're familiar with that, okay? So this is not something, this is something, again, that appears in textbooks in a different context, but in doing just these standard field redefinitions, okay, this basically is going to give you some stuff that you can exponentiate. It becomes, effectively, it only kicks in at one loop, and then you can show that it's, that all of the one loop stuff give you scaleless integrals, which vanish in dimreg, okay? You probably heard Anish say that, well, and Matthias, for that matter, last week many times, okay? Scaleless integrals vanish in dimreg. So as long as you use dimreg, you don't have to do this. An exercise which I haven't done, which I've always wanted to force students to do at some point, but it seems like it's cruel, is to do a simple field redefinition, show that your S matrix elements are invariant at one loop, where you don't use dimreg, where you use a cutoff or something, and then you have to keep track of this factor and show that they're equivalent. That seems like fun, type 2 fun. I think it's non-trivial. It's actually hard to show these equivalences at, even at tree level. You have to be very careful with minus signs because there's a lot of cancellations. Anyway, okay, I said more about that than I want. Point is, I want to be honest with you that it's there, but we can ignore it, okay? We're going to ignore it. So now we just have, and then let's relabel. So we have phi prime to phi. So we have z of j is integral d phi e to the I L prime of integral, L prime of phi plus j f of phi. Okay? Get a lot of exercise lecturing here. So we have this form of the path integral, okay? And we have now this form of the path integral. And exactly getting to the question that was asked, right? The only difference is the coupling to the source. So in that version, we have j phi. In this version, we have j f of phi. Everything else is the same, okay? You with me? Good. So we have coupling to the source. I keep writing too high. J phi versus J times F of phi. Okay, so that seems like a pretty big difference. And in fact, it leads to the differences in the correlators, as I said it would, okay? So, why doesn't the path integral care? The path integral cares. Why don't the S matrix elements care? Well, the S matrix elements, the critical thing, remember, with the S matrix elements is we did this LSE reduction where we want to pull out the poles, okay? So, the claim, this is very non-trivial, but this is where the action is, okay? This is the meat of the argument, is that the LSE reduction does not care if I'm taking functional derivatives that give me, with respect to J, giving me factors of phi, or giving me factors of F of phi, as long as I leave the following formula unchanged, okay? So the claim is that all the S matrix needs is that my field redefinition, going from phi to F of phi, doesn't change the interpolating formula. So all I need for LSE to stay invariant is the new field to be an interpolating field. What does that mean? That means that it interpolates the single particle states in the following sense. I'll write a formula, but this is why I was kind of going on before getting into formulas about this difference between the particle picture and the field picture and the tension there, okay? This is the fundamental formula that kind of maps between those two pictures. We often say this defines phi as an interpolating field for the single particle states. What does that mean? That means I have a single particle state, P, okay? That's a momentum eigenstate of a particle, of a scalar particle, and as long as this formula is non-zero, I can use phi to build my relativistic theory of the particles that exist in this state, okay? So, in particular, if I set the, again for simplicity, I set the wave function renormalization to 1, then the formula, it just gives me a plane wave factor, right? This is the standard interpolating field formula, okay? And here I could have an arbitrary coefficient. I'm setting it to 1, but of course, that coefficient is critical to be able to compute the S matrix at loop level. This is a part of the power of LSE, is that it tells you where to put those factors, okay? But that's not, the point for me is just that this is non-zero. So what I need is if I write my field redefinitions, phi is F of phi prime, looks like phi prime plus, I'll call it little f of phi prime, okay? So as long as I have this linear term in my field redefinition, then P of F of phi prime, 0, this matrix element, is P of phi prime, 0, plus P F of phi prime, 0. But this is just going to give me back this interpolating field formula, or this plane wave factor, okay, up to the wave function. This has higher powers of phi, so it vanishes on the single particle states. Okay, so this goes to 0, because if I put phi squared in there, I get 0. If that's not obvious to you, you can just check it with creation and annihilation operators quite quickly. Okay, and so I get back my plane wave factor, e to the IPx, which is non-zero. And again, if I were doing this in more generality, I might get some rescaling factors. No problem, I just include them in a consistent way in my S matrix. And so, so this is exactly the point, okay? There is a very big class of coordinate changes or field redefinitions that I'm allowed to do that don't change the interpolating field formula, okay? So even though I've screwed up completely the correlators, they look completely different than they did in the original theory and the redefined theory. Nonetheless, when I pull out the poles that correspond to external particles going on shell, right? I do this reduction where I'm basically taking the correlator and I'm pulling it to infinity, right? To generate the S matrix elements, and I'm extracting the part of it that contains the S matrix element. All that matters is this, because by the way, this gives you the propagator, okay? If I have this interpolating field formula, then I get the propagator factors that appear in that LSC formula and they don't change, okay? So this is why we're allowed to do field redefinitions without changing the S matrix. Well, good. So I was just about to say what other things F needs to respect. So indeed, this little f had better respect the symmetries of the theory in the sense that if this transforms in some representation, this better transform in the same representation. Otherwise, this equal sign doesn't mean anything, okay? So sort of built into this automatically is the idea of symmetry, right? If I added an index here, I better add an index here so it's covariant, okay? So absolutely, I need to be careful not to break covariance, okay? That's critical, right? And so then I put the same A's here and here. Additionally, it's not in this argument, but this had better be analytic in the fields and derivatives, okay? This had better be a polynomial, basically. Because, why? Well, when I wrote this Lagrangian, right, this L prime, I want this to be a local analytic quantum field theory, because that's all I know what to work with, right? I'm still interested in the class of theories that stay local. So for this to give me meaningful S matrix elements, this field redefinition better be restricted to give me a sensible Lagrangian. If my field redefinition I do here gives me a Lagrangian over here with 1 over h's or whatever, right? Like what I was finding when I was just doing that trivial redefinition from little h to big H, okay? Then I got a problem. I don't know how to calculate with that theory, right? I can't use my expansion in terms of creation and annihilation operators. I can't use any of the standard tools, okay? Maybe you could discover some new techniques for doing those calculations, but I'm not clever. I just know what Weinberg taught us to do, basically, okay? And so, so if I want to use all of the standard tools, right? If I want to follow textbook quantum field theory, I want to make predictions at the LHC, well, I better not screw up my symmetries, right? And I better not generate some crazy non-analytic Lagrangian. And in fact, that's really the whole game we're playing in these lectures, okay? I want to do this change of variables from HEFT to SMEFT, but it turns out, now you see, not only do I have this map from little h to big H, which already is leading to puzzles, as I just showed you, but it gets worse. I don't know what basis to use. Physics doesn't tell me what basis to use, okay? Maybe there may be some deeper fundamental picture for how to make this decision, but we don't know what it is. We just write down some variables, try to parameterize the most general possible Lagrangian that respects our EFT rules, degrees of freedom, power counting, symmetries. So there are many, many ways to do that. Each person in the room could pick a different basis, okay? We're all gonna get the same answers for our physical observables. That's the miracle. It's really quite remarkable. I mean, this is a non-trivial argument, okay? And you should worry about this. I implore you, especially the LSC reduction part. I mean, this is non-trivial. But nonetheless, if we just follow the rules, okay, then at the end of the day, if we're all careful with our minus signs and factors of 2, we all should agree on what the LHC would see, okay? So if you have your favorite HEFT Lagrangian you've been studying, and I want to know whether or not I can rewrite it as SMEFT, well, it turns out that there's an ambiguity. there's an infinite class of field redefinitions I in principle could do before I even make that map, okay? So let me check time, awesome. Let me highlight that for you, and that'll be the last thing we say today, okay? By the way, I won't write on the board, it's in the notes, but if you've never played with this, if this is a new idea to you, I asked Anish, he said he mentioned this in passing, but if this is a new idea to you, if you're interested in EFT especially, this is a big deal in EFT because changing basis is a whole industry, okay? By the way, Anish probably told you that they call it using the equations of motion, which is horrible terminology. It's extremely confusing. It turns out at dimension 6 that doing the this field redefinition is can be equivalent to applying the equations of motion to change the operators. Actually, in Anish's lecture notes, the ones that I reference at the end of my notes, he shows you that example in detail. It's very nice, okay? So if you're, maybe he did that last week. If not, I would definitely recommend going and taking a look at that. Yeah, give me just a second. But I just want to interject that what you're doing when you manipulate these Lagrangians is you're doing field redefinitions. Okay, the simplest one looks like applying the equations of motion, but that does not work when you go beyond dimension 6. And so if you really want to do this carefully, it's always writing formulas like this one, okay, and then applying them and turning the crank. That plus integration by parts are the two tools we have to simplify the Lagrangians. Yes, please. Yes. Yes. Yeah. No, what I mean is that we can, if you corner me later, we can pull up the details. But basically, what you can show is that field redefinitions of this type at leading order in EFT power counting, like at dimension 6, give you a factor which looks like you know, box phi plus m squared phi plus interactions. And so you can do a field redefinition basically that lets you swap the derivatives acting on phi, the two derivatives acting on phi, for polynomials in terms of phi at lowest order. So it looks like taking the tree level equations of motion and plugging them into the Lagrangian, okay, is a trick you can use to simplify the Lagrangian, because we all hate derivative couplings, right? They make life harder. And so the strategy is to reduce as many derivatives as possible without changing the physics. So people call this using the equations of motion, because that's the quick way to do the procedure. But what they're really doing is they're really doing a field redefinition when they use that procedure, okay? Applying the equations of motion is not something you can do, anyway, it doesn't generalize, that idea doesn't generalize. The generalization is you're just doing this, and you just want to use the freedom here to make your Lagrangian as simple as possible, okay? But one thing that I'm gonna try to convince you of, probably getting into it tomorrow, is if you do this in HEFT, then you try to map to SMEFT, and you're gonna get something that looks totally non-analytic, even if that map exists. So this freedom, you know, the thing that maybe you were trained to do, which is, oh, I've got my EFT Lagrangian, I need to reduce the derivatives, is actually going to, if you're asking a question about S-matrix elements, that's gonna make your life easier. If you're asking the questions we're asking here, can I then take that Lagrangian and map it onto SMEFT? You're actually completely obscuring the physics. So depending on your goals, you may want to do different things, okay? And there's a lot of freedom here, okay? That you can do, again, you have to follow the rules, but as long within the rules, there's still a ton you can do here. And I think, well, I probably will run out of time, but the last thing I wanted to do today was to show you a perverse example where exactly what I'm saying could be very confusing. Okay? But yeah, so if since you're asking about this equation of motion connection, I recommend Anish's notes from 2018. It's very clear there. Take a look, or we can look at it together, and if it doesn't make sense, you know, certainly come and find me. Yeah. Uh-huh. No, this is specific to dim. This is a non-trivial statement. This is specific to dimreg. Okay, and in order to see this, you need to play similar games that you do with the anomaly, where you sort of rewrite this into the path integral, and then you can see it kind of as in terms of diagrams and so on. It's not an easy thing to see. Okay, so this is one of this like kind of take my word for it. Probably would have to sit down for a while to convince yourself this is true. And again, it's only true in dimreg. It's not saying that it's just one. It's saying that it generates diagrams. It generates loop diagrams, okay? But all of those loop diagrams are scaleless. So if you used a cutoff, they'd give you something that you need to keep around. But if you use dimreg, then they go to 0. So it's 1 plus loop diagrams, basically, okay? That's the claim. But that's a non-trivial claim I'm making. I'm not proving that to you, okay? You should wonder, like, yeah. Okay, wonderful. So, okay, what do I want to say? So now we want to apply, well, any other questions? We don't have to rush. Okay, because the next thing I want to do is quickly say something just about polar coordinates, okay, that you may not have thought about before. So make a very simple point about polar coordinates, and then if I have 2 minutes at the end, or if you'll bear with me and I'll go late, I'll write, the last thing is kind of an invitation to get you excited about tomorrow. Yes, please. If you do that, then you will, if the SMEFT expansion exists, you'll get the same answers. The question I'm posing here is whether or not SMEFT, you can go to the SMEFT description at all. It may be the case, again, in my sort of circles diagram, right? There's this band where outside of SMEFT, where only HEFT lives, okay? So that's the claim, is that there are theories, and I plan to show you examples by the end of this, where that live in that band. Perturbative examples, I can write them down for you concretely, where you cannot write down SMEFT. It will not give you a convergent EFT expansion, okay? So that's really the thing. Absolutely, if you're in that region where both SMEFT and HEFT exist, then absolutely you can do, if you do analytic field redefinitions, you should be fine. Everything should come out the same, okay? But it's really trying to identify what lives outside SMEFT, okay? That's really the game we're playing here. And again, by the end of today, I'm gonna show you something that I hope will surprise you, okay? It certainly surprised me when I first saw it, and that will get you excited about tomorrow, okay? Yeah. Yeah, absolutely, absolutely. That's one of the... Absolutely, so yeah. One of the classes of models, indeed, is where there's extra electroweak symmetry breaking. Exactly as you say. So then little h is not the, also has to have some other degrees of freedom mixed into it, indeed. But we'll see exactly how that comes out of trying to make this map concrete in a way that's invariant under field redefinition. Okay, 5 minutes on polar coordinates, and then I'm gonna show you this fun example. So, and this gets to the question that came earlier about mapping, about the origin, okay, in polar coordinates. And because I'm rushing, and this is not so important, maybe I won't write all the details of these formulas, a couple of them are bulky, but they're in the notes if you want to see them. Okay, so how is this going to apply to our questions HEFT and SMEFT, okay? So let's just talk about 2D polar coordinates. Okay, so the manifold Notice I'm sneaking in some geometry terminology, right? We have a 2D manifold, R2, okay? It's just 2D flat space. Again, we've been doing this since, you know, I don't know, we learned this in kindergarten or something, right? Cartesian coordinates, polar coordinates. And so we have polar coordinates, r and theta. I make these jokes about, you know, how early we learned this, but I don't know if you've ever heard this from Leo Pandazayas at Michigan, but he claims that he learned Lagrangian mechanics in like junior high school or something in Cuba, because he was on some track, you know, they put people on tracks. I don't know, I know you guys have a crazy education system here too. You learn things super early, but I always, that one always stuck with me. It's like, okay, you got a jump start. Anyway, okay, so polar coordinates r and theta, right? And we write a line element, ds squared is dr squared plus theta squared r squared d theta squared. And then we have two sets of Cartesian coordinates. We'll call them C1, X1 and Y1, C2, X2 and Y2, okay? So let's work away from the origin. Right, that's where either the x and y's are 0 or the r is 0, okay? So away from the origin, we have invertible and analytic relations. So let's just pick something. So this is the standard thing, right? Or we have we could define this, why not, okay? Of course, this makes life harder, but nothing's stopping us. Notice, I mean, what am I really, the game I'm playing here, right, is I'm doing a field redefinition of R, okay? R goes to R plus R squared, right? That's very much like the kinds of things we do in EFT. So, and of course here I'm setting some length unit to 1, right, in order to make this dimensionally correct. So then we can just do the algebra, okay? We can map between these two sets of Cartesian coordinates. Okay, that's y. But this map is not real analytic at the origin because of this square root, right? This is a square root of 0. And that's from an analyticity point, right? That causes non-analyticities. Okay? And we can even see that if we compute the line element in both pictures, okay? So this is the thing I'm not gonna write in detail because I think I'm probably out of time at this point. Not quite, but yeah, it's not worth. But basically, of course, the first one just gives us standard flat space Cartesian coordinates, okay? The second one gives us something, there's a typo. Must be x2 squared plus y2 squared. Anyway, you can look in the notes if you're interested, or you could do the exercise, but already you see, right, in the line element, something goofy's going on at the origin, right? There's some, one over x's here. So this generates a non-analyticity in the metric, right? I'm assuming you have a little bit of experience with GR. If not, maybe corner me or ask in the Q&A. We can talk a little bit about these formulas because I'm going to use them starting tomorrow. But you know, from this line element, right, you get a metric. In this case, it's just the delta ij, right? It's just flat metric. Here, you would extract some metric. Of course, I didn't write all the terms, but you just pick off the coefficients, right, of the differentials, construct a metric, and the metric has non-analyticities in it, okay? So the metrics look very different in these two coordinate systems, but of course that's okay. A metric is not an observable, right? We need to use the metric to construct something, because the metric is a tensor, right? It transforms under coordinate changes. That's exactly what we're seeing here. So we want to construct something that's invariant. So the natural thing would be to compute, say, the Ricci scalar from this metric, okay? And indeed, what we find, so we take the Ricci scalar, so let's just take a general 2D line element. Well, it's not completely general, but pretty close. Okay, so of the form we're talking about, right? So this is just a generic line element. From here, we could compute the Ricci scalar. R of R is T prime squared over 2T squared minus T double prime over T. Okay? If you're not so familiar with this, this is like a really nice thing to do tonight. Okay? It's using Wikipedia. It's not that hard. It might take you an hour if you've never done it before, but basically taking this, read off the metric. Okay, it's trivially 1 and T, and then turn the crank and compute the Ricci scalar, because I'm going to do this in the EFT. Okay, exactly this kind of thing. You'll see very similar formulas appearing in the rest of the lectures. So then we can check our two cases. Okay, in flat space we had T equals R squared, and this gives us R equals the Ricci scalar equals 0, and there's no physical singularities. Okay, and you can check if you plug in the other T. There's no physical singularities, okay? But if we have instead, sorry, I said that wrong. We have T equals R squared. There's no physical singularities, okay? But when we have T equals R, and you plug into this formula, then you get R of R is 1 over 2 R squared, okay? So then R of 0 goes to infinity. Okay, so there's some physical obstruction at the origin. So it's exactly this kind of question, okay? We want to ask questions in a coordinate invariant way as much as possible so that we can find basically whether or not we have these analytic maps between their two different coordinate systems, okay? Because again, we're going to get back to physics, okay? This is taking a technical detour, but basically what I want to convince you of in the rest of the week is that we can frame this question in a way that avoids having to worry about all of these weird things that in principle we could do by doing field redefinitions, by introducing the ideas of geometry as a diagnostic, and then that's going to lead us to a very compelling physical picture for what theories live in that band outside of SMEFT. Okay? So that's the plan. And you might say, okay, this is just you goofing off with polar coordinates, and you're not impressed. So let me just write one more formula, 1.5, and leave you with that for today. And then of course we can chat. There's the Q&A and everything. But this is another nice exercise if you want, if you don't feel like sleeping. Something else to do, or something you can, of course, you can do all this stuff once you're back home. You know, by the end of this, I'm going to tell you all these like high-minded geometry. Oh, it sounds so fancy, but actually I'm a very simple guy. I like examples. So my collaborators are all the fancy people, and I would always say, I don't understand what you're saying. Can we do an example? So Zhao Chuan came up with this. Blew me away. I guess I could leave it as a homework exercise. Actually, I'm not going to do that. That's mean. But is this HEFT? Sorry. Can this be SMEFT? Okay. Is this a SMEFT? So that's my question. Okay. This does not look anything like SMEFT. I have square roots of h squared. That's not SMEFT. I have 1 over square roots of h squared. That's even worse. Okay. This is non-analytic at the origin, very much like my polar coordinate example, okay? What's going on? Could this possibly be SMEFT? I mean, if you hand me this and you asked me, especially 5 years ago, I would have said absolutely not. This is by definition violating all the rules of EFT. Nonetheless, I claim that if I go to the physical vacuum and I work with little h and I do a field redefinition, h goes to h1, which is h plus 1 over 4v h squared, okay? Very simple field redefinition. This becomes, in terms of capital H1 now, dh1 squared minus v tilde h1. It's the freaking standard model, okay? So that awful mess all reorganizes into kinetic term plus polynomial for the standard model. In fact, you know, if I set the potential to 0, I mean, it literally could just be free of field theory. You can completely distort by doing field redefinitions at the physical vacuum. Okay? So this is the problem, is that I can take literally the simplest possible theory and I can make it look like it's not an EFT. Okay? So again, you're working with your friends, you both have your HEFTs and you'd like to ask this question. Well, I don't want to have to work with HEFT. I want to tell my experimental friends who are looking at observables in terms of SMEFT how to map between what I'm finding in my calculation and what they should be looking for. And then you try to just do the map and you say, oh, SMEFT doesn't exist. But this was such a simple theory. I just added a heavy singlet scalar. It ought to, like, I'm very confused. Well, it is very likely that all that's going on is your calculation put you in some random field basis. And in that field basis, the map to SMEFT looks deeply flawed, looks non-analytic, blah, blah, blah. Okay? So that's the wrong test. Just doing this map that I showed you earlier is not good enough because of field redefinition ambiguity. Okay? So anyway, I hope now I've set up the puzzle, okay? And I've motivated you that you're going to be excited to see a field redefinition invariant way of talking about this stuff, which is namely we're going to appeal to geometry, like I kind of teased over there, and we're going to be able to frame this question, does SMEFT exist, as a geometric question, okay? And I'm going to show you how all that works, and then I'm going to tell you the implications, and that'll, well, I'm sure we'll go over time. I mean, that'll definitely take the rest of our time together, okay? So anyway, I'm going to stop there. How'd I do? 6 minutes. Sorry about that. Okay, I'm going to stop there. And I look forward to the rest of the week. Thanks so much for your attention and your questions. Oh, yeah. Yeah, so very good. So in these examples, there's actually some rescaling. So you do need to be careful. If you look at our paper, so by the way, I'm very heavily referencing a paper of mine with those collaborators called Is SMEFT Enough? Okay, it's long, but it has all this stuff in it. This example too, and there we're much more careful, and we show what that you have to be careful to keep track of the VEV of the original theory versus the V1 for the H1. Absolutely. Yeah, so you need to be careful about what this field redefinition also does to shift the vacuum. But because you're always doing phi goes to phi plus stuff, at worst it's just a rescaling. Right, so that's a part of the, and we'll talk about that a little more when we talk about the criterion for SMEFT existing. But yeah, it's a great question. I mean, that's definitely a part of the story. You have to be careful with that. Absolutely. Yes, please. Good, yes. Yes, then you need to include, right, so at some point in when I wrote that interpolating field formula, I said I was setting the wave function factor 1. But to do this in full generality, you need to leave that factor unfixed, and then that factor shows up in the LSC formula and exactly compensates for what you're worried about. So the S matrix elements indeed stay invariant as long as you include the appropriate wave function factors. And at some level, when you go from the Wick theorem derivation of the S matrix to the LSZ derivation, the Wick theorem derivation is nice. It's concrete. I understand every step. But unfortunately, it doesn't tell us where to put those wave function factors, right? That's why we introduce, at some level, operationally, we really introduced the LSC formalism mostly to just derive those rescaling, exactly those rescaling factors you're worried about when we go to loop level. So absolutely, if you're careful to include the most general form of the interpolating field formula, then you'll get the right answer. If you did phi goes to phi squared plus stuff, the interpolating field formula would be 0. So that you can't do, right? That definitely will change the S matrix elements. Yes? That's right. Well, it's really that, the funny thing about quantum field theory, the way we have come to teach it in the modern era is as a field theory, but that's really not the right, well, nothing's wrong with that, but I think I'm guilty of this too, but students lose track of the fact that the fields are not really the physical objects. What matters are the particles, right? Ultimately, we're not doing CFTs, we're not doing other things, okay? If we're doing perturbative quantum field theory, a la Peskin and Schroeder, then we are computing S matrix elements, or decay with. All we care about, right, are theories of quantum mechanical particle scattering, local theories of quantum mechanical particle scattering, right? And so the physical objects the observables are derived from the S matrix elements. S matrix elements aren't really observables, but right, the cross sections and generalized cross section, that's all coming, that's the observables of the theory. In fact, all the business about, say, renormalization, right, all these funny things that happen along the way in quantum field theory are all about the fact that we use fields, which are in many ways an inefficient tool for getting at the physics we care about, okay? It's just that they make locality manifest. If you asked me to take creation and annihilation operators and to build a local theory for you, I wouldn't know how to do it, right? It's only when I go to fields and I can write phi of x, and then I can write polynomials and derivatives of phi of x, then it's very easy to go back to creation and annihilation operators, right? You get some awful string of stuff with very carefully chosen relations so that your observables, for example, commute outside the light cone, right? Things like that are critical to getting a causal observables, okay? And so the fields are a tool, but they're not physical. And I think, it's in the title of every book, quantum field theory, and so we tend to overemphasize the fields themselves, but this whole thing about field redefinitions really, it reminds you that the fields are just a mathematical tool, okay? And you tell me. I mean, geometry is a step towards that, as you'll see. If we can frame everything geometrically, then we make some progress, but the geometry also has its limitations, as I'll explain, okay? The answer is, at some level, it doesn't matter. You pick your favorite basis. If you like to work with derivatives, then work with an EFT with lots of derivatives, okay? I don't like to work with derivatives because I'm bad at minus signs, so I try to eliminate them as much as possible, right? That gives me a different basis. I do field redefinitions to go back and forth. You're not wrong, I'm not wrong. Maybe everybody's wrong, I don't know. But, right, I mean, we get the same answer at the end. And so, so it doesn't matter, you just pick whatever's convenient for you, whatever you want to use, and you calculate, okay? Yeah. By the way, since I'm blathering, now I can blame my jet lag. I also want to just say, I don't have time to mention it, but I mentioned renormalization, it reminded me. It may not have necessarily come up in this school yet, but there's a very close link between EFT and renormalization. If you've not made that connection, then you should bug me about it over coffee or something. I think the right way to think about renormalization is in terms of EFT. And in fact, now when I teach field theory, I teach EFT. before I teach renormalization because they're the same idea. And EFT is way easier to understand. So if you're confused about renormalization, but you think EFT is cool, and you haven't made that connection, then you should bug me about that, okay? Anyway, now I'm really gonna stop. We can go to lunch. I'm happy to keep chatting with everybody. Thank you again for your attention.